Hello, my chemistry students. We are getting into Module 2 on ideal and real gases. And hopefully you see a lot of familiarity here or some review from your general chemistry days when you first talked about ideal gases. So we will review a little bit of those early concepts from Gen Chem and then move on to some topics that hopefully you've not discussed before. So in our first learning goal here, 2.1, we're just going to start it really simple by trying to understand the concept of an equation of state. So first, let's just ask, what is a physical state? So again, I said we're going to be real basic here. The physical condition of a sample based on its pressure, its temperature, its volume, and its amount, which hopefully I don't have to tell you what that letter N stands for, number of moles, right? So in an equation of state, we could take any one of these conditions, and if three of them are specified, so if any three are specified, then one is fixed, right? So for example, if we wanted to specify our equation of state to be a function of temperature, volume, and amount, then our pressure has to be fixed based on that amount according to some function. The famous function that we might remember from general chemistry is our ideal gas equation, right? P equals nRT over V. I know it's tempting to say PV equals nRT, but remember, we're keeping this as an equation of state. So we want all of those on one side of the equation and everything else on the other side of the equation. So we will see that there are other equations of state that will describe the behavior and physical state of a gas. But this is the most famous one. This is the easiest one to remember. So looking at our units for pressure, there's several we can choose from here. And I know that when we went over units, we talked about the SI. The correct one that we want to use is the Pascal. But we will also see the bar, the ATM, and torr quite a bit in this class as well. You don't have to memorize these kinds of things, but I think if you use these numbers enough, you accidentally memorize them, okay? So hopefully you accidentally memorize that, for example, 1 atmosphere is 101.325 kPa. If you don't, that's okay. We can look up the value. So moving on, just a couple of physicsy things to talk about with respect to our gases. So if we have two gases in containers with a movable wall, for example, they will be in mechanical equilibrium. So we remember that pressure is force divided by area. And that's where we get the Pascal from, right? If that's a Newton over a meter squared, then we know that that's equal to 1 Pascal. Of course, we could do that in terms of pounds per square inch, right? If I have a pound of force acting over 1 square inch, then we know that that is a PSI, a pound per square inch. Or our other unit that we often see in chemistry is the torr, named for Galileo's graduate student, Torricelli. And the invention of this unit comes from Torricelli creating the barometer. Okay. So, but first, if we ask, what is this mechanical equilibrium business going on? This is very happy, feel-good stuff. If we have this movable wall and two containers, if there's a high-pressure sample on one side and a low-pressure sample on the other side, the high pressure will exert a force over the given area of this movable wall until the two pressures are equal. Of course, if the two pressures are equal, the wall doesn't move anymore. And if the opposite side had high pressure, then the wall would move the other way. So there's a really good example of this, and that is, as I mentioned, the barometer. So if we have this container containing a pool of liquid where we have a tube submerged, and that tube is sealed to contain this liquid, we know that the atmosphere is always pushing on this liquid, right? If we've got this at atmospheric pressure. And this looks exactly like our mechanical equilibrium picture now. So then this liquid will now rise in this column to a certain height based on however much pressure, or really how much force over a given area is pushing on that liquid. So once these two things are in equilibrium, this liquid will always exist at a certain height. Torricelli found if you put liquid mercury in here, it will rise to 760 millimeters of mercury to give you one, let me try to write that again, to give you 1 atm, right? And of course, if it were a different liquid with a different density, we know that that would have a different height. Okay, additionally, another thing to talk about in our understanding of concepts of equations of state, thermal equilibrium. So we first start with what is known as the zeroth law of thermodynamics. If we have two objects in contact with each other of differing heat, heat will flow from the high temperature side to the low temperature side until they have both achieved the same temperature. So the low temperature isn't sucking heat away, rather the high temperature is giving heat away. If they're at equal temperatures, they will stay just that. And of course, if we reversed the temperatures, then we would see the opposite flow of heat. So this takes advantage of having two different types of containers, either a diathermic or an adiabatic container. So diathermic, if we kind of analyze that word, we would find that that means thermally conducting. Okay, so in other words, right, we can see that word right there. This is a diathermic wall. On the other hand, if this was an adiabatic wall, which is thermally insulating, then we would not see heat flow. This is an adiabatic system. Okay. So these are two words we are going to use quite a bit in this class. So diathermic, thermally conducting, adiabatic, thermally insulating. Okay, so hopefully that was some pretty good review of your physics and how that equates to the equation of state. I'll see you in the next video.